Thanks. At first, I'd just like to give a shout out to Hojin Jang, who, as a graduate student, did all the hard work on this project. He did a short postdoc at MIT and just started his assistant professor position at his alma mater, Korea University. And most of you know that CNNs do extremely well at object classification tasks. It's been claimed that they reached human level, although in recent years, work from my lab, Robert Garros, and others have shown how they are unusually brittle and frail to things like visual noise or blur or other challenging conditions. And this led us to ask whether the pervasiveness of blur in human vision might, due to sluggishness, so whenever you look at something in the distance, you have to accommodate your eye. There's a lag to that, depth of focus effect. So if something is far away and you're looking near or vice versa, things will be blurry. And our resolution in the periphery is also very blurry. All these factors, even though we think of them as nuisance variables that we want to get rid of, actually confer robustness to the human visual system. And if we train our AI models that way, might they too become more robust and more human aligned. And we did this by training 8 different CNNs from scratch. You see them listed down below. And we would train them either on clear images only, drawn from ImageNet 1000, or on a mixture of blur levels. In weak blur, if you can make that out, you see the distribution. Most of the images are clear, and then slightly blur ones come with lower frequency. And in the strong blur case, we had a variety of blur levels, each presented an equal number of times. And what we're going to do is we're going to look at these trained networks and see how well they can account for human fMRI data, look at their robustness and their various tendencies. So one of the data sets we analyzed first was this data set from Shu and Pashkam, where they showed clear, high-pass filtered and low-pass filtered images to participants in the fMRI scanner. And we can try to fit that data using representational similarity analysis, which is basically saying if we look at any of the, say, different objects that are being shown, any pair of objects, how similar are the, or different are the activity patterns in the human brain, and how similar or different are they in terms of the CNN models. And you can see that the blur-trained CNNs, shown in blue and purple, do much better at predicting human fMRI responses across all 3 conditions. And one thing that puzzled our reviewers is that it actually does better at predicting responses to high-pass filtered images, which the networks were never trained on. And this is because the blur-trained networks tend to confuse those high-pass filtered objects and in a more similar manner to humans than the standard DNNs. Now, we can move on to a different fMRI data set. This one was collected by us, where we looked at human behavioral and fMRI responses to objects in visual noise, pixelated Gaussian noise, and Fourier phase scramble noise. And again, we see an advantage for the blur-trained networks in accounting for these fMRI responses. That's also true for each of the individual conditions, clear, pixelated Gaussian noise, and Fourier phase scramble noise. I'm not going to show you, but we also do better at predicting responses in early visual areas of the macaque monkey. And we can talk about this robustness to noise, and this is kind of interesting. What happens if we actually look at performance with noisy or challenging stimuli? This is ImageNet C, which is a common benchmark with 19 different image distortions used to test DNNs and how robust they are. And for our blur-trained CNNs, you can see with the data shown here that blur training leads to better improvement, not in all conditions, but in 14 of 19 conditions, we see significantly better performance for our blur-trained CNNs. One thing that we found is that these blur-trained CNNs are tuned to lower spatial frequencies and show somewhat broader bandwidth tuning. So how about shape sensitivity? Robert Garros developed this very nice procedure where he would use AI to generate what he called these Q conflict images. There you see the texture of an elephant combined with the shape of a cat. Here I'm just showing some sample images that we used, and you can see how the standard, weak, and strong blur-trained CNNs focus on different properties. So this is a texture of a clock, but you see a bottle rendered above and a dog on the bottom, and you can see that the weak blur CNN can capture the cap of the bottle, and the strong blur CNN successfully captures the head and sort of the rear of the dog. Across all the image types, you can see the average performance on the far right, and human performance is shown with the gray diamonds. So we're still a long ways to counting for human-level shape performance, but you can see that blur training gets us there a good part of the way. So it's really make them more shape biased. And I'd like to end with just some sort of a short video. Let's see if this works. Let's see if I have sound. This is a little ad that was put together by Research Square when this associated paper came out. So you get a sense of that. The way they can do that for under $500 is that the video is generated by AI. Interestingly, it's a paper on AI models, and they just need to replace us with AI systems to do the research, and we'll have completed the circle. If you're interested in hearing more about this, you can go back in time and see my poster yesterday, or you can download the following paper. Thank you for your attention.